Welcome! In this session, we will explore an interesting graph theory problem titled Minimum Number of Vertices to Reach All Nodes. We'll break down the problem, analyze potential solutions, and guide you through the most efficient approach. Let's dive in and start solving. In this problem, we are working with a directed acyclic graph, or DAG, which consists of n vertices numbered from 0 to n1. Along with this, we're provided an edges array, where each edge is represented as a pair, from _i to _i. This means there is a directed edge going from vertex from _i to vertex to _i. The goal is to determine the minimum number of vertices required such that, if we start from these vertices, we can reach every other vertex in the graph. Essentially, we need to identify a set of vertices from which all other vertices are either directly or indirectly reachable. The result should be returned as an array of integers, and the order of these integers does not matter. To better understand the problem, let's look at an example. Suppose n is 6, and the edges array is given as 0, 1, 0, 2, 2, 5, 3, 4, 4, 2. Here, the output is 0, 3. This is because, starting from vertex 0, we can reach vertices 1, 2, and further to vertex 5 through the outgoing edges. Similarly, starting from vertex 3, we can reach vertices 4 and 2. Notice that all vertices in the graph are either included in this set or can be reached from these vertices. Therefore, 0 and 3 form the minimum set needed to cover all nodes. Now, consider another example where n equals 5, and the edges array is 0, 1, 2, 1, 3, 1, 1, 4, 4, 2. The output here is also 0, 3. Starting from vertex 0, we can reach vertex 1, and from 1, we can reach vertices 4 and 2. Similarly, starting from vertex 3, we can also reach vertex 1, which again leads to 4 and 2. Since vertex 2 is already reachable from vertex 4, 0, and 3 are sufficient to ensure all vertices are covered. This demonstrates how the solution identifies the minimal set of starting points. The graph has some specific constraints and edge cases to consider. First, the graph is directed and acyclic, meaning it has no cycles. If the edges array is empty, no vertex can reach any other, so the output should include all vertices from 0 to n1. For a graph with only one vertex, such as when n equals 1, the output is simply 0, because there's only that one vertex. Another edge case arises when all vertices except one have incoming edges. In this situation, the result would be that single vertex, as it serves as the source for all other nodes. To solve the problem of finding the minimum number of vertices to reach all nodes in a directed acyclic graph, DAG, we first consider a brute force approach. The intuition here is straightforward. For every node, we perform a traversal like depth first search or breadth first search to determine which nodes can be reached starting from that vertex. By iterating through all nodes and marking their reachability, we can identify the minimal set of starting nodes required to reach every other node in the graph. However, this method has significant drawbacks. Since we are performing a traversal for each node, the time complexity becomes n plus e, where n is the number of nodes and e is the number of edges. This makes the approach computationally expensive and inefficient, especially for large graphs. Moreover, in the special case of a DAG, this redundancy becomes even more apparent, as the structure of the graph allows for a more targeted solution. Recognizing these limitations leads us to explore a more optimized approach based on graph theory. The optimized approach relies on a crucial observation about the structure of a DAG. In such graphs, nodes with incoming edges are already reachable from other nodes. The key insight is that nodes with no incoming edges, those with an integrity of 0, must be included in the solution. These nodes cannot be reached from any other vertex, so they serve as essential starting points to ensure all nodes are covered. To implement this, we follow a simple three-step process. First, we calculate the integrity for each node, which tells us how many edges are directed toward it. Next, we identify the nodes with an integrity of 0. Finally, we return this set of nodes as our answer. This approach has clear advantages. The time complexity is reduced to n plus e, as calculating integers and filtering nodes are both linear operations. The space complexity is also efficient, requiring only an array to store integers and a result list to hold the nodes with 0 integrity. This makes the solution both scalable and efficient. The optimized approach is ultimately the better choice because it leverages the inherent properties of the DAG structure to significantly simplify the problem. Rather than performing multiple redundant traversals as in the brute force method, we focus solely on indegrees to identify the critical nodes. This reduces the time complexity to O, n plus e, which is essential for handling graphs with up to 10 to the power of 5 nodes and edges. While the brute force approach is easier to conceptualize, it becomes impractical for large inputs due to its high computational cost. On the other hand, the optimized approach may require a deeper understanding of graph theory, particularly the significance of indegrees, but it is far more efficient. By taking advantage of the DAG structure and avoiding unnecessary computations, this method guarantees both correctness and scalability, making it the most suitable strategy for solving this problem. To dive into the algorithm, the first step is to truly understand the problem. Our objective is to determine the key requirement of the problem. For instance, if we're dealing with a graph traversal problem, we need to clarify whether we're solving for connectivity, finding the shortest path, or identifying the minimal set of starting nodes to cover all nodes. Next, it's crucial to define the input format. Is the graph given as an adjacency list, matrix, or an edge list? This impacts how we process the data. Similarly, we need to specify the desired output. Are we returning the number of connected components, a list of nodes, or simply a Boolean result? Once the problem is clear, we begin with an initial approach. Starting with a brute force solution helps establish correctness. For example, in a graph traversal problem, we might iterate over all nodes and use DFS or BFS to verify reachability. This step also uncovers edge cases and ensures the algorithm handles simple inputs correctly. After that, we refine the approach using observations. For example, if the graph is sparse, adjacency lists might be more efficient, while union find can help for connectivity problems. The ultimate goal is to optimize time complexity without sacrificing correctness. Finally, we implement the optimized algorithm with the refined approach in mind. Breaking the algorithm into smaller, modular subtasks is an effective way to ensure clarity and testability. For example, you might start by parsing the input, then building the graph representation, performing the necessary operations like traversals or union find, and wrapping up with the output generation. By structuring the solution this way, each step becomes easier to debug and validate independently. Once the core implementation is complete, it's essential to test thoroughly with edge cases. For instance, consider how the algorithm performs on an empty graph, one with a single node, or a fully connected graph. Disconnected graphs with multiple components also provide valuable insights into the solution's robustness. Another key consideration is the choice of graph representation. Adjacency lists are more space efficient for sparse graphs since their storage scales with the number of edges, O, V plus E. On the other hand, adjacency matrices allow for faster edge lookups at the cost of higher space requirements, O, V squared. The representation choice directly impacts the efficiency of your algorithm and should align with the problem constraints. Choosing the right traversal method is critical. Depth-first search, DFS, is ideal for exploring all nodes within a connected component, while breadth-first search, BFS, is better suited for shortest path problems in unweighted graphs. Both methods are fundamental tools in graph algorithms. For problems involving connected components, union find is a powerful technique. To optimize union find, we use path compression and union by rank, which bring the time complexity down to nearly constant time, specifically O, alpha, n, where alpha is the inverse Ackermann function. As you design your solution, remember to account for edge cases. Disconnected graphs, isolated nodes, and self-loops are all scenarios that can challenge the correctness of the implementation. Additionally, the choice of data structures has a significant impact. For instance, adjacency lists are efficient for sparse graphs, where the number of edges is much smaller than the square of the nodes. When performing BFS, a queue is indispensable for maintaining the correct order of exploration. In Python, this can be implemented using collections.deque. Similarly, for DFS, a stack is used to track nodes during depth-first exploration, and a simple list with append and pop operation suffices. Continuing with the stack for DFS, it's an effective tool for keeping track of nodes during depth-first exploration, and its implementation in Python is straightforward using a list. Union find deserves special attention as well. It is particularly efficient for determining connected components in a graph. By using an array for parent pointers and applying path compression along with union by rank, you achieve an optimal structure for connectivity checks. Now, let's consider a concrete example to understand the algorithm. Suppose you're given a graph with 4 nodes and 4 edges, represented as an edge list, 0, 1, 1, 2, 2, 3, 3, 0. The first step is to parse this input and construct an adjacency list. For this graph, the adjacency list would look like this: 0, 1, 3, 1, 0, 2, 2, 1, 3, 3, 2, 0. This representation is both compact and efficient for traversing the graph. Once the adjacency list is ready, the next step is to initialize a visited set and select the traversal method, such as DFS. Starting from node 0, you explore the graph, marking nodes as visited as you go. In this example, the visited set would eventually contain all nodes, 0, 1, 2, 3. This confirms that the graph is connected since all nodes are reachable from the starting node. After completing the traversal, the algorithm verifies reachability and outputs the result, such as stating that the graph is connected. Turning to complexity analysis, the time complexity for graph traversal, whether DFS or BFS, is O, V plus E, when using an adjacency list. For union find, the complexity is O, E asterisk alpha, V, where alpha is the inverse Ackermann function, making it extremely efficient. As for space complexity, storing the adjacency list requires O, V plus E, and the visited set or union find parent pointers require O, V, making the algorithm scalable for large graphs. In conclusion, the choice of algorithm and data structures depends heavily on the problem constraints, such as the size and sparsity of the graph. It's vital to test your solution on a variety of edge cases to ensure it's robust and handles all scenarios correctly. While optimizing for time and space complexity, it's equally important to maintain code readability and modularity. Breaking the problem into smaller, testable components not only simplifies debugging but also ensures each part of the algorithm is well implemented. By following these principles, you can design efficient and reliable solutions for a wide range of graph problems. This solution addresses LeetCode problem number 1557, minimum number of vertices to reach all nodes. The problem involves a directed graph represented by n nodes, 0 to n1, and an edge list, where each edge is directed from a source node to a destination node. The goal is to find the minimum set of vertices such that all nodes in the graph are reachable from at least one of these vertices. The key insight is that a node with incoming edges can be reached from other nodes, so these nodes do not need to be part of the result set. Conversely, nodes without incoming edges must be included in the result because they cannot be reached from any other node. The solution begins by initializing an empty set, has_incoming, to track nodes that have incoming edges. Then, it iterates through each edge in the input edges list and adds the destination node, edge 1, to the has_incoming set. This step identifies all nodes with at least one incoming edge. Finally, the solution constructs the result as a list of all nodes from 0 to n1 that are not in the has_incoming set. These nodes are guaranteed to have no incoming edges and must be included in the result. This approach is efficient, with a time complexity of O, n plus m, where n is the number of nodes and m is the number of edges. The space complexity is O, n, due to the use of the has_incoming set. Overall, the solution is optimal and well suited for handling large graphs within the problem's constraints. This is the Java implementation of the problem minimum number of vertices to reach all nodes. The logic mirrors the provided Python solution. It leverages a hash set to track nodes with incoming edges and iterates through all nodes to identify those without incoming edges. The key differences include Java-specific syntax, explicit type declarations, and the use of list integer for the input graph representation. In this problem, we aim to find the minimum number of vertices needed to reach all nodes in a directed graph. The graph is represented by nodes labeled from 0 to n1, and a list of directed edges. The key insight here is that any node with at least one incoming edge can be reached from another node. Therefore, the only vertices we include in our result are those that don't have any incoming edges. To illustrate this, consider a simple example where n equals 6 and the edges are provided as 0, 1, 0, 2, 2, 5, 3, 4, 4, 2. We'll start by initializing an empty set called has_incoming to keep track of all nodes with at least one incoming edge. Initially, this set is empty. Next, we populate the has_incoming set by iterating through each edge in the edges list. For every edge, we take the destination node, which is the second element of the edge, and add it to the set. For example, when processing the edge 0, 1, we add node 1 to has_incoming, resulting in 1. Then, for 0, 2, we add node 2, updating the set to 1, 2. Repeating this for the remaining edges, we eventually get 1, 2, 4, 5. Now, to find the result, we look at all nodes from 0 to n1 and exclude those in has_incoming. In this case, the nodes are 0, 1, 2, 3, 4, 5, and excluding 1, 2, 4, 5 leaves us with 0, 3, which is the output. Let's consider another example with a smaller graph. Here, n equals 2, and there is only one edge, 0, 1. Again, we start by initializing an empty set has_incoming. As we process the single edge, we add its destination node, 1, to the set. This gives us has_incoming equals 1. To determine the result, we take all nodes from 0 to n1, which are 0, 1, and exclude those in has_incoming. The only node left is 0, making the result 0. This illustrates how the approach works even for very simple graphs. Now, let's look at a fully connected graph where n equals 4, and the edges form a cycle, 0, 1, 1, 2, 2, 3, 3, 0. As usual, we initialize the has_incoming set to be empty. Iterating through the edges, we add the destination nodes to the set. After processing all edges, the set contains 0, 1, 2, 3, as every node has at least one incoming edge. To find the result, we take all nodes 0, 1, 2, 3, and exclude those in has_incoming. Since all nodes are in the set, the result is an empty list. This indicates that no single vertex is needed to reach all nodes, as the graph is fully connected. The underlying approach to this problem relies on the observation that nodes with incoming edges can always be reached from their respective source nodes. Thus, the only nodes we need in the result are those without incoming edges. This is achieved by iterating through all edges and marking the nodes that have incoming edges, which allows us to efficiently identify the minimal set of source nodes. The time complexity of this solution is O, n plus e, where n is the number of nodes and e is the number of edges, making it highly efficient for large graphs. To analyze the time complexity of our solution, we need to break it into two main steps. First, we build the has_incoming set. This involves iterating over the list of edges, which contains m edges, where each edge represents a connection in the graph. For each edge, we extract the destination node and add it to the set. Since adding an element to a set is, on average, an O(1) operation, the entire process of iterating over m edges and updating the set takes O(m) time overall. Next, we use a list comprehension to identify the result nodes. This involves iterating through all n nodes and checking whether each node is not present in the has_incoming set. The membership check for a set is an average O(1) operation, so iterating over all n nodes also takes O(n) time. Combining these two steps, the total time complexity becomes O(m) for processing the edges plus O(n) for checking the nodes, resulting in O(m plus n). Now let's consider the space complexity of the solution. The first major contributor is the has_incoming set, which stores all nodes that have incoming edges. In the worst case, every node in the graph could have an incoming edge, so the set would contain up to n nodes, requiring O(n) space. The second contributor is the output list, which stores nodes without incoming edges. In the worst case, none of the nodes have incoming edges, meaning all n nodes would be included in the output list, again requiring O(n) space. Finally, the input edges list, which is provided as part of the problem, uses O(m) space to store the edges. When we combine these factors, the total space complexity becomes O(n) for the has_incoming set, O(n) for the output list, and O(m) for the edges, resulting in a total of O(m plus n). When comparing this optimized approach to a brute force method, the differences in efficiency become clear. A naive solution might involve constructing the entire graph, either as an adjacency matrix or as an adjacency list, and then performing a full traversal, such as a breadth-first or depth-first search, starting from each node to determine the minimal set of starting nodes. Constructing the graph as an adjacency matrix would require O(n squared) time, or O(m), for an adjacency list. More significantly, performing a traversal from each of the n nodes would require O(n asterisk) m plus n time in the worst case, as each traversal could take O(m plus n). This results in an overall time complexity of O(n asterisk) m plus n for the brute force approach. Furthermore, the space complexity of a naive solution could be as high as O(n squared) for an adjacency matrix or O(m plus n) for an adjacency list. By contrast, our optimized solution avoids traversals altogether. It identifies nodes without incoming edges simply by iterating over the edges list and checking the nodes. This reduces the time complexity to O(m plus n) and the space complexity to O(m plus n), making it significantly more efficient in both aspects. Finally, let's analyze the best, average, and worst-case performance of this algorithm. The time and space complexities remain consistent across all cases, as the algorithm always processes the complete edges list and checks all n nodes. This means the time complexity is always O(m plus n), regardless of the structure of the graph. To justify this mathematically, the for loop iterating over the edges list contributes O(m) operations, and the list comprehension that iterates over the n nodes and performs constant time membership checks contributes O(n) operations. Since these two steps operate independently, their complexities add up linearly, resulting in O(m plus n) time. Similarly, the space complexity is determined by the has_incoming set, which can hold up to n nodes, the output list, which can also contain up to n nodes, and the input edges, which requires O(m) space. Together, these factors result in an overall space complexity of O(m plus n). One common mistake to watch out for is not accounting for disconnected graphs. If the graph isn't connected, you can't assume all nodes are reachable from a single traversal. This is especially important for undirected graphs, where it's easy to overlook isolated components. Another frequent oversight is ignoring edge cases. For example, what happens if the graph has no nodes, just a single node without any edges, or contains self-loops? These scenarios can easily lead to runtime errors or incorrect results if not handled explicitly. Additionally, using inefficient traversal techniques, like repeatedly checking visited nodes in an adjacency list, can introduce unnecessary computational overhead. Optimizing with appropriate data structures, such as sets or arrays for tracking visited nodes, can make your solution more efficient. Finally, remember that directed and undirected graphs behave differently. Reachability depends on edge direction in directed graphs, so it's critical to respect the problem's constraints when determining which nodes are accessible. Overcomplicating the algorithm is another pitfall to avoid. Beginners sometimes use nested loops unnecessarily, even when a single traversal, such as DFS or BFS, would suffice. This can inflate the complexity to O(n squared), when the problem could be solved in O(n plus m). Now, from an interview perspective, one key insight is that many graph problems are fundamentally about understanding connectivity. Familiarizing yourself with algorithms like UnionFind, BFS, and DFS is invaluable, as they are core techniques for solving such problems efficiently. Another important skill is pattern recognition. Many questions revolve around reachability or cycle detection. Recognizing this early can help you choose the right algorithm. Additionally, always be mindful of time complexity. Interviewers may ask you to optimize your solution or explain the trade-offs between time and space. Lastly, thorough testing is crucial. Make sure to test your solution on edge cases like empty graphs, graphs with cycles, or extreme structures like star graphs and chains to ensure robustness. Now let's explore related problems that share similar concepts. For instance, LeetCode 200, Number of Islands, focuses on identifying connected components in a grid, essentially a variation of graph traversal. Another example is LeetCode 547, Number of Provinces, which is about determining connectivity in an undirected graph, often solved using DFS or UnionFind. LeetCode 997, Find the Town Judge, introduces a directed graph problem where understanding reachability and degree counting plays a key role. Lastly, LeetCode 261, Graph Valid Tree, combines multiple graph concepts by asking you to verify both connectivity and acyclicity. These problems are great opportunities to refine your understanding of graph algorithms and to practice applying them in different contexts. When it comes to alternative approaches, union find, or disjoint set union, is an efficient choice for connectivity checks, with near constant time complexity for union and find operations. However, it requires additional memory to manage parent and rank arrays. Breadth first search, or BFS, is another option, particularly useful for finding the shortest path in unweighted graphs. The downside is its higher memory consumption due to the queue used for traversal. Depth first search, or DFS, is more memory efficient when implemented with an adjacency list, but it can lead to stack overflow on very deep graphs. To avoid this, consider using an explicit stack for large inputs. Finally, the choice between adjacency matrices and adjacency lists depends on the graph's density. Adjacency matrices provide O(1) edge lookups and are better for dense graphs but consume O(n)² space. On the other hand, adjacency lists are far more space efficient at O(n+m) and are ideal for sparse graphs. Understanding these trade-offs will help you select the best approach for your problem. Thank you for joining us in solving the minimum number of vertices to reach all nodes problem. We covered the intuition, an efficient algorithm, and its complexity analysis. Remember to practice graph problems to strengthen your understanding of traversal techniques and edge properties. Don't forget to subscribe for more solutions. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!